Hi everyone, I'm Dan Fullerton, and in this video we're going to take a look at the 2017 AP Physics C Mechanics free response questions. Now, I have not seen the released scoring guide yet. It'll probably be a couple months before that comes out, so it's quite probable I miss a point or two doing something silly, but hopefully walking through these fairly quickly and in the way that I would attack them if I were taking the exam at least gives you a pretty good idea of how to go about taking on these sorts of problems. So with that, let's dive in and see how it goes. The first question is an Atwood machine problem where we have two blocks connected by a light string that passes over a frictionless pulley of negligible mass, a magic pulley, an ideal pulley, as shown in the figure. The masses of the two blocks can be varied, but M2 is always greater than M1. And the first thing they want us to do is to draw free body diagrams for the two separate blocks. So I would start with mass 1. There's our block, nice little dot. We have tension from the string up, and we have its weight, M1G down. And of course, the tension has to be greater than the weight because we know it's going to accelerate up. M2, we also have tension, has to be the same, equal and opposite forces. And since there's no tension in the pulley, it's frictionless, it has no rotational inertia. So the tension has to be the same in the string, but this time the weight, the force of gravity on M2 has to be greater than the tension because it's going to accelerate downwards. And what I'm going to do is I'm going to define some directions. I'm going to call this our direction of motion for our positive y direction as we go around that. Now for part B, using the forces that we drew, use Newton's second law in order to solve for the acceleration. And it tells you you have to do a separate equation for each block, which is just kind of silly because you could certainly do this in a system fashion and solve for it probably a little quicker. I'm not a big fan when they tell us how to solve the problem, but I'm sure somebody had their reasons for doing this, so let's just do it their way and get the right answer. Let's start by looking at block 1. Now I'm going to write a Newton's second law equation. Net force in the y direction equals MAY. Because we defined up as our positive y direction, this will be T minus M1G must equal M1A. Or I could solve for tension. T therefore equals M1A plus M1G. And I'll call that equation 1, because I think we're going to need that in a minute if I've done a couple of these types of problems before. Block 2, same basic idea, but now we're defining down as our positive y direction. So in this one, net force in the y direction is going to be M2G minus tension equals M2A. But look here, tension we just said is M1A plus M1G. We can place this in place of tension right there in order to solve this. So taking this a little bit further, M2G minus M1A minus M1G, just replacing tension here with M1A plus M1G equals M2A. And now it's just a little bit of an exercise in algebra to get the acceleration all by itself. We could write here that G times M2 minus M1 must equal A times the quantity M1 plus M2. And then solving for acceleration, that'll be M2 minus M1 over M1 plus M2 all times G. Now, next, what they're going to end up asking us is to use this sort of equation to draw a graph and solve for the acceleration due to gravity, a really common type of physics question. So the first thing I'd note before we go a whole lot further is we can make this fit the equation of a line. Remember, the equation of a line is y equals mx plus b. Well, I don't see any plus b part over here in this form, so the y-intercept must be 0. But y, if we put acceleration on the y-axis, that'll work. It's kind of helpful if g is our slope. That's what we're solving for, so let's make that m. That means that all of this in here must be must be our value we're going to plot on our x-axis. So y equals xm, y equals mx. Same thing, just switching the order of those variables. If we plot m2 minus m1 over m1 plus m2 on the x-axis, acceleration on the y, the slope of whatever we get, should be our acceleration due to gravity. So that's going to be helpful next when they tell us, here is the data that they've shown. What would you plot in order to go find the acceleration due to gravity? So on the vertical axis, I'd plot A. On the horizontal axis, I'd plot m2 minus m1 over m1 plus m2. And you can fill in that fourth row there. Should come out to be first data point around 1/3, second point 0.2, 0.412, 0.193, 0.167, so on. Fill those in, and then when you go to make your plot, should look something kind of like this. And I'm just going to do this fast. We have acceleration on the y, acceleration measured in meters per second squared. On our x-axis, we have the quantity m2 minus m1 divided by m1 plus m2. And as that's going to be mass divided by mass, that's unitless. Go ahead and plot your points. Careful to make sure you get them in the right spots. I don't know, something kind of like that. Draw your best fit line. And to go find the acceleration due to gravity now, that is just going to be the slope of that line that we just drew. Slope is rise over run. Pick 2 points on your line, not necessarily data points. y2 minus y1 over x2 minus x1 comes out to be about 9.6 meters per second squared when I made my graph, and I imagine yours should look pretty similar to that. So that covers us for part E. Now for part F. Well, before we go any further, let's give ourselves a little more room. Part F, we're going to adjust this Atwood machine and put M1 on a nice magic table that doesn't have a whole lot in the way of friction for now. Smooth horizontal table, it says. For the same values of M1 and M2 is the magnitude of the tension in the string when the blocks are moving higher, lower, or equal to the magnitude when the blocks were moving in the first experiment. Well, if you think about it, our free body diagram now for M1 is going to look like this. There's M1, it'll have tension. M2 will look pretty similar. Tension and M2G. Notice now, for the first one, tension is equal to M1A when we apply Newton's second law, not M1A plus M1G. So the weight of M1 is no longer supported by the string, therefore there's less tension. So I would answer this one as it's definitely going to be lower. And for part G, the value determined for the acceleration due to gravity is lower than in the first experiment. Explain. Well, I would probably look at something, the simplest explanation might be the friction between the table and M1 isn't taken into consideration. Friction would reduce the measured acceleration since it opposes motion. And given that this is a time-constrained test, I'd probably stop there. You could go on a lot further, but I bet you probably don't need to. That should cover it. So with that, let's take a quick break and we'll come back to question number 2. All right, here we are with number 2. Now we've got a block at the top of an inclined plane. It's going to hit a nice smooth horizontal surface and eventually run into a spring and compress it. So a conservation of energy problem like you've probably seen before. First thing they're going to have us do is find the speed of the block just before it collides with the spring. Well, when our block starts off, it has all gravitational potential energy, which is equal to mgh. Oops, my screen's not behaving here. Let's try that again. Equal to mgh. And right before it collides with the spring, all of that energy has become kinetic energy. So now we can depict that in the form 1/2 mv squared. Solve for the speed v, and you get the very common square root of 2gh, which I'm sure you've seen before in physics. So A1, pretty straightforward, and you might have even been able to have said that answer without even going through the derivation. Do the derivation anyhow, get all the points. Now, A2, is the speed halfway down the incline greater than, less than, or equal to half the speed at the bottom of the inclined plane? All right, now we're getting into something a little more interesting. Well, if you think about it, the speed halfway down is kinetic energy, but now you're only using half of this mgh that you had. So the speed when you're halfway down is going to be square root 2gh over 2. where this divided by 2 is inside the radical, because that was our gravitational potential energy that's converted into the kinetic energy. As opposed to the speed at the bottom, half of the speed at the bottom, speed bottom, let's call that half, is going to be square root 2gh divided by 2, where that divided by 2 is outside the radical. Well, what's the difference between these two? This is less. Since that 2 is in the radical, we could also depict this on the left-hand side as 2gh divided by 4. Compare that over here to 1/2 square root of 2gh. Obviously, this one is less. So over here, we could say the speed halfway down the inclined plane is going to be greater than 1/2 the speed at the bottom of the inclined plane. All right, part B, derive an expression for the maximum compression of the spring. Well, again, we've got a conservation of energy problem. What we have is 1/2 mv squared. The kinetic energy is equal to mg delta h, the change in gravitational potential energy, which is then going to become the elastic potential energy in the compressed spring, 1/2 kx squared. So take this part of the equation, let's solve for our maximum compression x, and come up with square root 2 mgh over k. So there's your maximum compression. Again, just some algebraic manipulation. Part C gets a little more interesting again. Find an expression for the time from when the block collides with the spring to when the spring reaches its maximum compression. And you could make this really simple or really complicated. Being rather simple myself, I'm going to start with the simple solution. If you recognize that this is a spring block oscillator, a horizontal spring block oscillator, where the block is going to be going back and forth, compressing, decompressing, going back and forth. It starts out at the equilibrium position when it just comes into contact with the spring. When it's at its maximum compression then, that's 1/4 of the periodic motion of the spring block oscillator, or 1/4 the period. So really, for answer C, for part C, what we're finding is 1/4 the period. All we need then is the formula for the period of a horizontal spring block oscillator, which happens to be 2 pi square root m over k. And we want 1/4 of that, so that just becomes pi over 2 square root m over k. And if you recognize that this is the time we're talking about, all of a sudden that problem isn't so bad. Could spend a lot of time doing it in other methods, but I'd certainly go for the quick one, as you've got a timed test here that's rather challenging. Now, for part D, we're going to get more involved again. Now we're pulling out the big guns, getting into some calculus. So let's give ourselves a little more room here. Okay, the block is again released from rest. When it reaches the horizontal surface, it's moving with some initial speed, v0, but there's a resistive force, and that resistive force is proportional to the square of the block's velocity. So the retarding force, the drag force on it, is going to be beta, some positive constant with units of kilograms per meter times the square of the block's velocity. Okay, once we have that, we're asked to write a differential equation for the speed of the block on that surface in terms of our general variables and fundamental physical constants. Now, the free body diagram, we've got our block, and we have bv squared, our resistive force. Up and down, we know those are going to be equal. It's not going to go accelerating up off of the surface or down through it, so we don't have to worry about the y direction for now. So I would write Newton's second law, F net in the x direction, which is minus beta v squared, must be equal to the mass of our block times its acceleration in the x direction. But acceleration is the first derivative of velocity with respect to time, so that becomes minus bv squared equals m dv dt. There's our differential equation. Can rearrange this a little bit to make it a little bit friendlier. I'd probably look at doing something like, let's see, v squared plus m over b dv dt equals 0. But now we want to separate our variables, get all the v's on one side and all our variables of time on the other. So we could do that. We could write this as v squared over dv is equal to minus m over beta, and dt in the denominator. I'm not sure I like those differentials in the denominator, so let's just flip them on both sides. So we get v to the negative 2 dv equals minus beta over m dt. And that looks like something we can start to play with here. We can do some calculus on. So let's see if we can't solve this. If we integrate both sides, the integral of v to the negative 2 dv must equal the integral of minus beta over m dt. And our limits of integration, in terms of velocity, we're starting at v0 and going to some final value v. And in terms of time, we're starting at some t equals 0 and going to some final value t. From there, well, the integral of v to the negative 2, that's just going to be v to the negative 1 over negative 1, and we have to evaluate that from v0 to v. In the right-hand side, beta and m are constants. Integral of dt is just t, so that's going to be minus beta over m t evaluated from 0 to t, which is also just t. So that's not too bad. A little bit more rearrangement here, and we can say that, well, let's plug in our variables here. V to the negative first over negative 1 minus v0 to the negative 1 over negative 1 equals minus beta over m t, or 1 over v equals 1 over v0 plus beta over mt if we multiply through by negative 1. And that v is our velocity as a function of time. And I think we did what they asked us to. Yeah, that meets the form that they were looking for. So we've done part D2. Solve that for that specific form. Now, however, it wants us to graph these. All right, we should be able to do that. A little bit of common sense. And again, you could go into a lot of detail trying to make these perfect, but as it's a timed test, I think I would just go for the quick and easy version. And if you miss a point or two, that's all right. You can always come back and spend more time later. Make this as a function of time. This is a function of time. This is a function of time. And we've got position, we've got velocity, and we've got acceleration. So quickly looking at position, starting at some position 0 and heading out a little bit further and slowing down as you go. For velocity, starting off at some v0 and heading down this way, v0 heading to some other velocity later on, decreasing, starting to approach that v equals 0. And acceleration, starting with this high negative acceleration and eventually heading in there to 0. And you could spend more time. I think I'd stop right there and get your points, move on. Come back later if you have more time. So we'll call that the end of question 2, and we'll come back to question 3 in just a moment. All right, and on to our final question down the home stretch. Now we've got our rotational motion problem. Got to have one of those. We've got a cylinder sitting on a ramp that's on a table that then is going to be launched onto the floor as a horizontally launched projectile. It sounds kind of familiar. Conservation of energy, rotational motion, probably seen something similar. As we start this problem, it wants us to calculate the total kinetic energy of the cylinder as it reaches the horizontal table. And I would do this by conservation of energy. Since we're not worried about losses due to friction, we can just say that the change in gravitational potential energy must all be manifested in the kinetic energy of the cylinder when it reaches the table. So the big trick is going to be finding the height of that ramp. And thankfully, it gives us the hypotenuse 1 meter and the angle 30 degrees. Well, 1 sine 30 degrees, sine 30 is 0.5, so 1 meter times sine 30 is half a meter. That ramp must be half a meter high. And we could start dealing with things like taking into account the radius of the cylinder and stuff like that. We're time crunched. Let's just get the main idea, work on the basics here. So for 3, part A, I would say the kinetic energy total is equal to the gravitational potential energy it had at the top, which is mgh, Our mass was half a kilogram, g 10 meters per second squared, and we'll approximate, and height half a meter, how far that ramp extends up off the table, or the change in vertical position of that cylinder. 0.5 times 0.5 is 0.25 times 10 is 2.5 joules. There's A. Check. B. Find the total angular velocity of the cylinder around its axis at the moment it reaches the floor. And that shouldn't be too bad, because if we find it when it reaches the table itself, it's not going to change while it's in the air. So really, we could look at this in terms of conservation of energy again. The kinetic energy at the bottom must be equal to the translational plus the rotational kinetic energy of the cylinder. So kinetic energy bottom equals translational kinetic energy plus rotational kinetic energy, which is going to be 1/2 mv squared, the translational kinetic energy, plus 1/2 I omega squared, the rotational kinetic energy. We also know we can relate translational velocity to rotational velocity using v equals omega r. So we can put that into our term for the translational kinetic energy to write 1/2 m omega squared r squared plus 1/2 capital I, our rotational inertia it gives us is 1/2 mr squared, and we still have an omega squared. It must be equal to our total kinetic energy at the bottom. This implies then that 1/2 m squared r omega squared r squared plus 1/4 m squared omega squared r squared equals the kinetic energy at the bottom. Well, that's just going to be 3/4. So 3/4 m omega squared r squared must equal that total kinetic energy, 2.5 joules. Or then, solving for omega, that's going to be 4/3 times our total kinetic energy, 2.5 joules, divided by mr squared, which was, let's see here, our mass, 0.5, r, 0.1 squared. Put all this together and I come up with about 667 radians squared per second squared. Radians, of course, really being unitless, but I like to leave them in there because I'm easily confused. If that's going to be, oh, that's our omega squared, not omega. So if we want just omega, we take the square root of that. Square root of 667 is around 25.8 radians per second. All right, there's part B. We're getting there. For part C, calculate the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. All right, well, the rotational kinetic energy, when it hits the floor, we can calculate that. Kinetic energy rotational is 1/2 I omega squared. We've had some practice with this, which is 1/2 times I, 1/2 mr squared times omega squared, which is going to be 1/2 times 1/2 times 0.5 times 0.1 squared, all times our omega squared, which is going to be 25.8 radians per second. We just figured that out. Comes out to be about 0.83 joules. Now to find the total kinetic energy at the floor, well, that's going to be the total change in gravitational potential energy, because ultimately the initial condition, it's all gravitational potential energy, and the instant before it hits the floor, it's all become kinetic energy of various forms. So the total kinetic energy is equal to the gravitational potential energy at the top, which is just going to be mgh, where we have a mass, 0.5 kilograms, g still 10 meters per second squared, and our total height is the height of that incline plus the height of the table, 1.25 meters, comes out to be right around 6.25 joules. We're asked to find the ratio of these, so we want this kinetic energy, the rotational kinetic energy, divided by the total kinetic energy, or 0.83 joules, over 6.25 joules, comes out to be about 0.133, or 13.3% of the total kinetic energy is rotational when it's at the floor. And that covers us for part C. Part D, find the horizontal distance d. All right, a little bit of a break here. We've got a basic horizontal projectile. All right, some algebra physics. Let's give ourselves a little more space as we look at part D. Let's find out how long that's going to be in the air. Vertically, its initial velocity is 0 since it's launched horizontally only. Delta y is the height off the table, 0.75 meters, and ay is going to be 10 meters per second squared, calling down our positive y direction for this part of the problem. So looking for time, we can use our kinematic equation, delta y equals v naught y t plus 1/2 ay t squared. And one of my favorite tricks here, v initial in the y direction is 0, so that whole term becomes 0. We can now rearrange this to solve for t and find that t is going to be equal to 2 delta y over a, take the square root of all of that, which is going to be the square root of 2 times 0.75 meters divided by 10 meters per second squared, or about 0.387 seconds, the time it's in the air. Well, once we know the time it's in the air, horizontal is pretty straightforward. Horizontally, there is no acceleration. Gravity only pulls down. So the displacement in the x direction, which is our distance d, is just v naught x times t. In this case, we know that that vx is omega r. That's going to be omega r times t. Omega was 25.8 radians per second. R, the radius of our cylinder, 0.1, and our time, 0.387 seconds. Put that all together, and I get just about 1 meter. Okay. Moving on to part E, we're now going to do this with a sphere with the same mass and radius, but the rotational inertia of the sphere is 2/5 mr squared, as opposed to 1/2 mr squared for the cylinder. So the first question, E, says the total kinetic energy of the sphere when it reaches the floor compared to the total kinetic energy of the cylinder when it reaches the floor. Which is greater? Well, here we have to just think about conservation of energy. The total before and total after, if it's the same mass, it doesn't matter. We're not losing any along the way. There's no non-conservative forces we have to deal with, so they have to be the same. They're equal. The total kinetic energy at the floor has to be the same whether it is the cylinder or the sphere. How much is translational and rotational might be different, but the total has to remain the same by the law of conservation of energy. Part E2, though, now we're getting into it, is the rotational kinetic energy of the sphere greater than, less than, or equal to the rotational kinetic energy of the cylinder? Well, here, if we take a look at the rotational kinetic energy of the sphere when it's at the floor, so this would be E2, that's going to be, for the sphere, 1/2 I omega squared, but I now is 2/5 mr squared times omega squared, so that's going to be 2/10 m omega squared r squared. Whereas before, for our cylinder, we had 1/4 m omega squared r squared. So it's less when we have our sphere. Therefore, the kinetic energy that's rotational on the floor for the sphere would be less than. And finally, for part E3, is the horizontal distance the sphere travels from the table to where it hits the floor greater than, less than, or equal to the horizontal distance it travels to where it hits the floor? Well, in this case, since the previous one was less than, we're going to choose greater, and here's why. You have less kinetic energy rotational for the sphere, meaning that more of it must be translational kinetic energy, which is manifested in more horizontal velocity. So if it has a higher initial horizontal velocity in the same time in the air, it has to go further. So the sphere will travel further compared to the cylinder horizontally. D will be greater for the sphere. All right, hopefully that at least gives you an idea of how to attack some of these problems. Hope the exam went well for you, or if you're studying for one down the road, that this gives you a good head start on what sort of questions might be asked. Thank you so much for your time, and make it a great day.